We're going to look at the Spectral Centroid, which is a measurement of brightness, and you'll be using this in the project to control FM synthesis parameters. And what I want to do now is talk about what is the spectral centroid, how is it computed, and we'll also look carefully at the Fourier transform and interpreting the coefficients that come from that. And finally, we'll look at some example code. So remember, the Fourier transform looks like this. We're taking the signal x sub I, multiplying it by cosines and sines of different frequencies. Those frequencies are controlled by this parameter k, which is the coefficient, an integer coefficient, integer subscript for, or index for these coefficients are the real coefficients and x the imaginary coefficients. These points, x sub k and r sub k, are evenly linearly spaced in frequency because you saw, let's go back, you saw that k is a factor in the frequency term here. And the question now is, what do these coefficients really represent in terms of frequency? And this is addressed on the left-hand side of this busy slide, and the right-hand side of the slide is about how these coefficients are actually packed into an array of real numbers, which is the result that you get back from a Fourier transform when you call it in Nyquist. Okay, so back to the coefficients. We start with n samples of audio, and we compute n over 2 r coefficients and n over 2 x coefficients. Actually, it's n over 2 plus 1 because the coefficients go from 0 up to n over 2. The n over 2 coefficient represents half the sample rate, which is the Nyquist rate, the highest frequency that you can have in that signal. And therefore, the points x sub k and r sub k, since they're linearly spaced from 0 up to sample rate over 2, and there are n over 2 intervals, we can derive this equation for the frequency represented by each value k. And that simplifies to just k times the sample rate divided by n. Therefore, the sample rate divided by n is the frequency spacing. So between bin number 23 and bin number 24, there's a frequency difference of sample rate over n. Maybe I should say, what does it mean to say that a bin has a frequency? Remember, the Fourier transform is doing a spectral analysis. It's analyzing the frequency content of the signal, and it's producing a discrete set of coefficients that represent the energy at each of those frequencies that gets analyzed. So what we're doing now is we're talking about what are the exact frequencies used in the analysis, and so that's what this formula up here gives us. The kth coefficient corresponds to an analysis of the frequency k times sample rate over n. So for example, if we have a 44 kilohertz signal and we're doing a 1024 point FFT, then the bin size, or the bin width, is, or the spacing between these coefficients, which are called bins, is 44 kilohertz divided by 1024, or 43 hertz. Another way to look at this is, if I wanted to know what is the frequency content of this spectrum at 430, that would be 10 times the frequency spacing, so I would look at coefficient number 10. Or I'd look at the real coefficient and the imaginary coefficient at index 10. Now, these coefficients are not packed in any obvious way, or there is no clear, obvious way to pack these coefficients into an array. So we have to pay careful attention to that. First of all, the FFT takes in n samples of real signal, 1024 samples, let's say, and it outputs 1024 samples, 1024 coefficients. These numbers have to be the same because FFTs are invertible. So if you have a 1024 point analysis, essentially the spectrum, the signal and the spectrum have a dimensionality of 1024. And you have to have this, for this transform to be invertible, you have to have the same number of dimensions on the input and the output. So here's how we pack these coefficients. First of all, the first element of the array, in other words, at location 0, is r sub 0, the cosine of 0 component. Cosine of 0 is just 1. It's not actually oscillating, but we're actually integrating all of the samples. That's the first coefficient. That's because of this integration. This is sometimes called DC, or direct current component. It's really measuring the offset from 0 of the overall signal. After that, you might expect to find x sub 0 in the array, but x sub 0 corresponds to sine of 0, which is 0. So x of 0 is always 0. It's not really a degree of freedom. It's not part of this dimensionality, and so we just don't even put it into the array. So the first, location 1 in the array is r sub 1, and location 2 is x sub 1, and then we just alternate real and imaginary and fill out the array until we get to the last pair of coefficients, the r and x, with subscript n over 2. This is the Nyquist frequency, and it turns out there's only one Nyquist component, which again is the real or the cosine component. The reason for that is sine, because it starts at 0. If you look at what happens to a sine wave running at the Nyquist frequency, it starts at 0. The next 0 crossing is exactly at the next sample, and the next 0 crossing is at the next sample. So all the samples get multiplied by the 0 crossings, and they're all 0. So again, it's 0, and we ignore it. That way, even though we have n over 2 plus 1 pairs of coefficients, since 2 of them are 0, we actually have n over 2 pairs of actual data, which means we get n points packed into this array, as we expect. All right, so now you know how coefficients are packed into arrays. You'll definitely have to review this if you're ever directly trying to pull out some frequencies of an analysis and make sure you get it right. But you can refer to the slide. Now, the next thing to look at is when we're doing spectral analysis, usually we're not actually interested in the real or the cosine part versus the sine part. These are the same frequencies, just calculated with different phases. And so what we really are interested in is, let's throw out the phase and just what would be the amplitude if we added those signals together. So it turns out the calculation is no, you do not add the real plus the imaginary part. You take the Euclidean distance. So in other words, the square root of the real part squared plus the imaginary part squared at any given coefficient k. And that forms what we call the amplitude or magnitude spectrum, whose coefficients are a sub k. And the magnitude spectrum actually has n over 2 plus 1 points because we have a 0 coefficient and an n over 2 coefficient. We use the magnitude or amplitude spectrum to compute the spectral centroid. So finally, we get to the spectral centroid, and we can talk about what it is and what it means. The spectral centroid is just a weighted average where the weights are the frequencies of the bins. So here, and I switched to index I guess because I'm a computer scientist. We can use I for index. So this is the index into the array or into the amplitude spectrum. and we take I times the width of the bin, and so that gives us the frequency corresponding to the amplitude sub I. And then we normalize that by dividing by the sum of all A sub I. And that's a weighted sum called the spectral centroid. Let's look at a picture of that. I think this to me makes everything much more clear. This is the amplitude spectrum of some signal. Again, it's the frequency axis, it's amplitude versus frequency. And if we could cut this shape out on a piece of uniform cardboard and try to balance it on a ruler, and we find the frequency point at which this whole shape balances, that would be the spectral centroid. So that's what this weighted average is doing. It's actually finding the balance point. And if it's balanced, that means there's kind of equal amount of low frequencies to high frequency energy. As high frequency energy increases, the spectral centroid moves to the right. It gets greater. When that energy goes away, the spectral centroid moves to the left. It gets lower. So the spectral centroid is often used as a measure of high frequency, or brightness would be the best perceptual term. Now, let's think about going back into the time dimension. The spectral centroid can vary over time if we're taking short-term transforms, short-term spectral estimates. So in this plot, imagine that shape that we just looked at starting at time 0, and as we move through the signal and take our analysis window and step it through the signal, measure the spectrum later, the short-term spectrum later in the signal versus earlier, the signal might change and the spectral centroid might change. So if we plot just the spectral centroid as a function of time, and I tried to indicate that here on the graph, then that would be a time-varying measure of local brightness in the signal. So that's what we're going to use in the project to control the depth of modulation in FM. And I'd like to switch now to Nyquist to go through a couple of examples. The first thing I'm going to do is play what will probably be an amusing sound. Okay, so I'm going to take that cow sound, analyze the spectral centroid, and use that to control depth of modulation in FM. You can see plotted here the spectral centroid as a function of time, and if we look at the code for that, we're just calling spectral centroid calculation sc-calc from a library that's a part of the project, analyzing the sound into SC, and then we pass SC scaled and offset, transformed however you want, to form a modulation signal for the depth of modulation. Here you see mod comes in as a parameter to simple FM. Mod is then used to scale the modulating oscillator here, and we have a classic FM carrier modulation ratio is 1:1, pitch, because we see pitch here and pitch here, and you heard the results. So I'm not going to do all of these, but let's look at the third example here, which is taking a pre-recorded beat, and let's listen to that first. Now, what do you think that's going to do to the spectral centroid? Well, remember that an impulse has a very, an ideal impulse has a completely flat spectrum, equal amplitude at all frequencies. Now, what you heard doesn't really have impulses, but every time there's a drum hit, even a bass drum hit, has a very sharp onset, which is kind of impulse-like, and that generates very high frequencies. So every time there's a hit in uh, in audio that generates a beat or a strong onset, that increases the spectral centroid. And so when we do the analysis, we will see, first of all, we'll see a plot, and we'll also hear this very metrical rhythmic variation in the spectral centroid, which is reflected by through the depth of modulation of an FM sound. Okay, we're going to go out with an example synthesized from frogs, and you can read the code and look into this in greater detail yourself.